Hello, welcome to Week-10 live session of NPTEL's Introduction to Semiconductor Devices course. I'm Om Maheshwari, and today we will solve some questions that will help you with your exams as well as your assignments. So let us begin. So in this week, mainly we'll be looking at the technology scaling as well as short channel MOSFETs. So I will begin with, since we are taking this session early, I'll begin with a small overview of the course content for this week so that it is easier to follow the questions. So MOSFET scaling was initially uh, realized by Dennard. So this is also called Dennard scaling. So in this scaling, basically we have a scaling factor alpha or zero point 0.7 where we try to reduce the vertical and lateral dimension by alpha, or alpha is zero point 0.7. So L changes to zero point 0.7 times L, W changes to 0.75 times W, T of changes to zero point 0.7 times T ox, like that. Similarly, we also reduce the supply voltage VDD. VDD changes to zero point 0.7 times VDD, and threshold voltage changes to zero point 0.7 times VP from one technology node to next one. And we increase the doping concentration by alpha. Substrate doping changes to and substrate doping by zero point 0.7. So here is a list of all the different parameters that change. So laterally, the lateral and vertical dimensions reduced by 30%, like W changes to zero point 0.7 times L and T ox by zero point 0.7 times. Supply voltage and threshold voltage are also reduced by 30%, that is zero point 0.7 times scaling in those two. So the die area, that is W into L, it changes by 50%. So and from one technology node to next one, your area is reducing by 50%. So it's zero point 0.7 times zero point 0.7 is 0.49. So 50% reduction in area, or 51% you can say. Total gate capacitance, it also reduces by 30%. That is, it scales zero point 0.7 times, which is C ox plus epsilon ox by T ox into WL. So this is zero point 0.7 times, this two are also zero point 0.7 times, these cross. So your total gate capacitance reduces by 30%. The gate capacitance per unit area increases by 40%, which is simply epsilon ox by T ox, which is 1 by zero point 0.7, which is 1.43 times it increases. Current reduces by 30%, and delay in circuit, T delay, which is CV by I, is everything here reduces by zero point 0.7. So delay in circuit reduced by 0.7%, 0.7 times, so 30% delay. Power dissipation reduces by 50%. It's CV square by delay, right? So zero point 0.7 into 0.7 into zero point 0.7 by zero point 0.7, which is 0.49. So power distribution reduces by 50%. So in scaling, we are trying to double the number of um, transistors almost every 2 years. This is also called as Moore's law. So this is just a graph that shows the technology scaling roadmap, how with time the technology nodes are progressing, and uh, let's say from 250 nanometers to 180 nanometers CMOS node. These are CMOS technology nodes. Uh, there's zero point 0.7 scaling in the naming also. So 250 into zero point 0.7 is 180, then zero point 0.7 times 130, 90, 65, 45, all up to till 5 nanometers in 2020s. And now uh, this year we are at 3 nanometer technology node, and next year we will transition to 2 nanometer technology node. So when we scale the supply voltage, we are reducing VDD to zero point 0.7 times VDD. So our threshold voltage is also reducing to 0.7 times VTH. So it creates a problem because if threshold voltage is reducing, your off current is increasing, right? And what you want is you want a higher ion by I off ratio. We want it to be more than 10 to the power 6 or 7. Like we wanted more than that. But when you are reducing the scaling, your short channel effects increase and your off current is actually increasing. This creates a problem that we have to manage. So with scaling, our transistor density is increasing. The complexity to even make realize these smaller transistors is also uh, becoming challenging, but the cost per transistor is reducing. So this is just an example of a 32 nanometer technology SRAM cell has this area, and this is compared to a red blood cell. So it's like almost hundreds of times smaller than the red blood cell. Okay, so now let's talk about the short channel effects, which is a very important part of this course. So short channel effects, so these numbers typically don't mean much, but yeah, typically long length is considered more than 1 micrometer for modern transistors, and basically these transistors follow square law theory, and their channel length is much larger than the depletion layer width of the source and drain junctions. So like this is the L channel length, which is much larger than the depletion region created at the source and drain junctions, so that we can directly ignore the contribution of these in your channel length. But in short channel, these play a significant role, and actually these reduce your channel length, which causes short channel effects. So what happens in a long channel versus short channel MOSFET? If you see in a long channel MOSFET here on this side, it follows the square law theory. So current increases with VGS minus VT square. This is the square law theory. So if you see in this ID versus VDS curve, if we are increasing VGS, the current increases quadratically almost, right? But here in this side, this is for a short channel MOSFET. This is again ID versus VDS. But if you are increasing VGS here, your current is not increasing quadratically. It's almost linearly increasing now here with VGS. So this is a big difference in the short channel effect. This is caused due to velocity saturation. So when this saturation happens due to pinch off, you have this quadratic dependence of VGS on ID. But if the this saturation happens due to velocity saturation, then this VGS has a linear kind of dependence on ID. So this just shows two graphs. This below one is a short channel MOSFET, and our top one is a long channel MOSFET in a same 180 nanometer technology node, and it shows like it has some velocity saturation effect. And we have already seen what is velocity saturation. Basically, VD is nu times E. So VD is linearly dependent on electric field, where mu is constant. But this, as electric field keep on increasing, the this velocity saturates. It does not linearly increase with electric field anymore. And this is due to various kinds of scattering. And this electric field basically is increasing. What it means is, as your channel length in a MOSFET is reducing, so your VD that you're applying is dropping in a smaller region. So your electric field is increasing. Thus, lateral electric field is increasing. And due to that, at higher electric field, you see this velocity saturation effect. Thus, your current reduces compared to longer channel MOSFETs. Okay, so there's one more thing such as channel length modulation. The channel length modulation means when you are applying here VD, then this depletion, since this N plus and P, this is reverse bias when you're applying positive VD. to saturate the transistor. This pinch off is happening here. Okay, but this uh, depletion region is increasing, and you can no longer ignore this depletion region. So your L changes to L minus delta L, and this actually increases your current. Your current is not no more exactly constant. It increases a bit in the saturation region, whereas it is much more like a constant, behave like constant current source for long channel MOSFETs. In short channel MOSFETs, this there is slight increase in this current with VDS, which was not the case earlier. So this is called channel length modulation. So our ID site equation is modified such that we had this earlier, right? Mu Cox Vg W by 2L VGS minus VT whole square. So we had this factor 1 plus lambda VDS, and this lambda is channel length modulation parameter. New ID is L upon L by delta L, right? So ID is 1 plus delta L by L, ID dash. So there is some increase here. So basically this is happening why? Because your this L is changing to L minus delta L. And this is also because you can at this short channel lengths now you cannot ignore the effect of this depletion width. These depletion widths are comparable to your channel length now. So you cannot directly ignore them. Okay, so short channel effect has also its effects on the threshold voltage. So generally threshold voltage reduces with short channel effect. So that happens again because of these depletion regions only. So your this depletion charge you have QD bulk, which is this one, then QD source and QD drain. So when you have a shorter channel, the contribution of this QD source and drain remains constant, but QD bulk reduces because you're reducing this length. But these junctions are not getting shorter. So this is actually what is controlled by the gate, QD bulk. These depletion charges are controlled by source and drain. So the contribution of the gate here is reducing. Gate control is reducing. So due to the presence of depletion charge by source and drain already in the small channel, their threshold voltage is reduced because now you require a very small VTA gate voltage to bring depletion here because a lot of depletion is already there from the source and drain junctions. That's why your threshold voltage reduces. This is also known as charge sharing. Your charge is being shared by source and drain. So as your channel length reduces, your threshold voltage decreases. Another effect is narrow channel effect. Now in short channel devices, if you reduce the width, so what happens is, so this is the width direction, and in this direction you have your length. So here the depletion is also on the sides, right? On around the sides under the oxide here. So here what happens is, as your width is reduced, the relative contribution of these sides compared to here increases. So basically, the total depletion charge here is, let's say, in this rectangular portion is QD, and this sides is QD dash. So if you are reducing W, this QD will decrease, but QD dash will not change. So this at shorter W, this QD dash becomes significant, which actually requires a larger potential to uh, bring this depletion charge. So your threshold voltage increases as your width is reducing. So with length, your threshold voltage reduces. With width, your threshold voltage increases. So another very important short channel effect is gain-induced barrier lowering. So this is a band diagram of a MOSFET. So you have source, drain, and gate. So if you take a cut line here, so you get a Venn diagram like this, right? This is N plus P, N plus. So this is N side, this is P side, this is N side. So how electrons come into the channel is you apply a gate voltage VG here. This barrier reduces. This easily allows electrons from source to go here. And then when you apply a gate potential, drain potential and drain, electrons from channel go towards the drain. So when what happens is in a short channel device, in a long channel device, let's say when you're applying a drain voltage, this side will go down, right? The bands on this side will go down. But in a short channel device, when you have channel very short, so this barrier is also reducing. This barrier, you see, this is the barrier, right? Between this N side and P side for the electrons to come. This barrier is also reducing when you're applying a gate, a, a drain voltage. So drain is actually reducing, lowering the barrier here, which in turn reduces your threshold voltage, which is undesired effect. We do not want the transistor uh, to to flow more current with drain voltage. We want it to have a constant current with drain. But this is basically reducing your gate control. We want a higher gate control. Gate should have the control over the channel. Uh, but here you can see the drain is having more control over the channel as this barrier is being reduced by the drain voltage, so more electrons can enter here. Okay, so what is the effect of this drain-induced barrier lowering? So in a large channel MOSFET, if you are changing the VDS, you have this almost same current in the subthreshold region for same VDS. But in the short channel MOSFET, there is this shift, this increase in this current, or your off current is actually increasing when you are applying a larger VDS. This is due to drain-induced barrier lowering. There's this almost parallel shift in the threshold voltage, which is not the case in a long channel MOSFET. In a long channel MOSFET, the threshold voltage and off current is unaffected by VDS. So whatever scaling that we discussed till now, that zero point 0.7 scaling and everything was valid for some technology nodes, but later on, uh, after 130 nanometer of CMOS technology, this scaling was not very successful. So we needed more different kinds of scaling, so also known as equivalent scaling. So in equivalent scaling, we did the reduction in dimension, but also introduced new materials and some new effects, like from the CMOS technology from 130 to 90 nanometer, we introduced strained silicon. What it meant was the source and drain were made of silicon germanium. Now, due to the latest mismatch of silicon germanium and silicon in the channel, there was uh, due to the latest mismatch, there was a strain in the silicon, which actually uh, actually helped to boost the mobility inside the channel. Due to strain, there was mobility uh, change in the mobility, and this mobility helped to improve the current. Similarly, at 45 nanometer node, we had high K metal gate structure. So instead of using SiO2 at the oxide, we use SiO2 plus a high K material. So the to reduce the gate tunneling, because there were limit to scaling the silicon dioxide, it was very thin already, and reducing it further would have resulted in the direct gate to channel tunneling. So to reduce that, we used a high K or high K material as oxide. Or high K means like it has epsilon more than SiO2. So SiO2 has high epsilon of 3.9, and high K, which is HFO2 mainly, has an epsilon of around 22 to 25. So this helps to have almost 6 times thicker oxide without uh, reducing the gate capacitance. Then there were like more transitions for 3D scaling. So we went to uh, better devices from high K, stained silicon, and everything to we finally went to 3D devices from planar to 3D. So this is 3D devices that was introduced from 20, 28 or 28 nanometer technology by Intel. So this is sorry, 22 nanometer technology by Intel. This is FinFET. FinFET has gate on. So here the channel gate just covers the channel from the top side. Here the channel will be on all its three sides of the fin, and gate will is surrounding on all three sides. So it basically improves your gate control and improves your electrostatic performance. Then we can have more fins so that we can have better control. And now, uh, so this helps us to improve. So from planar to trigate, you see, for constant ion, we are having much lower leakage current. So your ion by ion ratio is improving for FinFETs or trigate FETs. And your delay is also reducing because your current is increasing. So in future, in the next, actually in 2 nanometer technology, we will have gate around nanosheet FETs as the uh, transistor architecture. So instead of FinFET, what will happen is in nanosheet is the gate is surrounded. So this uh, the channel is this sheet of silicon, and the gate is on all four sides around it. Okay, so now let us look at the questions. So just give me a moment. Okay, so now let's start with the questions. The first question is, consider N-channel MOSFET where the lateral and vertical dimension WL are reduced by 20%. Both the supply voltage VDD and threshold voltage are also reduced by 30%. When this transistor is connected to a load capacitor, it is found the capacitance and delay are reduced by 30%. The dynamic power dissipation reduced by what percent? Please answer this question. Okay, so I hope you guys have solved this question. So I'll quickly go through it. So power dissipation is the dynamic power dissipation is P d is C V square by time delay. So we know that C changes to zero point 0.7 times. V also changes by zero point 0.7 times, and time changes by also zero point 0.7 times. So this will cancel. So your PD changes to 0.49 times P. So the reduction is 1 minus 0.49 is 51. So there is 51% reduction in power dissipation, dynamic power dissipation, which is 51. Next, we have the evolution of various technology nodes over the years is given in the figure below. Comment on the gate capacitance per unit area in the technology node 250 nanometer to 9 and 90 nanometer. Consider alpha as the scaling factor. So you have to tell when you go from 250 nanometer to 90 nanometer, how is your capacitance, gate capacitance per unit area is changing. So your Cox is epsilon ox by Tox. How does it change when you go from 250 nanometer node to 90 nanometer node in terms of alpha? Okay, so I hope you guys have solved it. So this is a very simple problem. As you know, Tox reduced by zero point 0.7 times for every technology node. So when you're going from 250 to 180, your COX is changing, becoming 1 by alpha times, let's say, then 180 to 130, it's again becoming 1 by alpha times, then 130 to 90, it's again becoming 1 by alpha times. So from 250 to 90, your COX is becoming 1 by alpha cube times. So COX 90 is 1 by alpha cube of COX 250. This is the relation that we have to find. Okay, next question. Given below are two statements regarding the characteristics of a short channel MOSFET. Typically, the channel lengths of a short channel MOSFET are much larger than the depletion width of the source and drain junctions. The current in a short channel MOSFET shows significant deviations from the square law theory. So you have to tell which are true and which are false. So first one is obviously true. The channel length for short channel MOSFET are much larger than depletion width. This is false. It is the whole concept of short channel MOSFET, the problems of short channel effects that we have. That is due to those depletion regions being comparable to the channel lengths in the short channel MOSFET, which cause reduction in gate control and threshold voltage reduction and increased control of the channel of on by the drain. So that those are the problems that are actually caused by the comparable size of depletion widths compared to the channel length in short channel MOSFETs. Second one is the current in a short channel MOSFET shows significant deviations from the square law theory, which is true, where we saw right in ID versus VD. So if this is quadratic in long channel, it is linear in short channel. So first is false, second is true. Option B is correct. Next one, again based on the statement 2 of the previous question, please solve this. Okay, so the question is in the figure below, VDS versus IDS for two MOSFETs are plotted for a gate voltage VGS is a 1.8 volt. The W by L ratio of both MOSFETs is equal. Identify the type of MOSFET corresponding to the curves below. So obviously MOSFET 1 is long channel and MOSFET 2 is short channel. So option 2 is correct. This is due to velocity saturation. Next question, what is the primary mechanism responsible for the reduction in threshold voltage in short channel MOSFETs? This is drain induced barrier lowering rate. Same short channel MOSFET we saw in a long channel MOSFET when we apply drain voltage VD here, and short channel in a short channel MOSFET when we apply the same drain voltage. You see there is a reduction in this barrier which reduces the threshold voltage. This barrier basically controls the threshold voltage. That is how much gate voltage you need to apply to easily allow the electron to flow. But this barrier is already lower due to this drain voltage, even without doing anything with the gate voltage. We are losing gate control and the threshold voltage is reducing in short channel MOSFET, which is due to drain induced barrier loading, DIBL. Next question. Which of the following is a direct consequence of the narrow channel effect NCE in MOSFETs? So we have seen this. What is narrow channel effect? So this is your width, you have oxide here. So you have some extra depletion on the sides also here, other than the center. So when your width is reducing, these parts do not scale. So you need more gate voltage to deplete these parts compared to this part as width reduces. So your VT increases. This is narrow channel effect. Increased threshold voltage as channel width decreases. This narrow channel effect. Next question. The question is, strained silicon is used to improve MOSFET performance. How does it enhance device characteristics, particularly in terms of carrier mobility? We saw this, right? During equivalent scaling around 90 nanometer CMOS technology, strained silicon was introduced. So what strained silicon did was your source and drain were made of silicon germanium, which induced some strain in your channel that enhances its mobility, which improves the current. So answer is increases current drive by enhancing carrier mobility. Next question. The use of high-K dielectrics in MOS transistors is motivated by the need to reduce the gate leakage while maintaining high capacitance. Which of the following is a consequence of high-K dielectric in place of SiO2 in terms of band diagram? The band gap of high-K material is larger than that of SiO2. The equivalent oxide thickness EOT decreases while maintaining the same capacitance. The effective electric field across the gate is higher. The conduction band of high-K materials is lower than that of SiO2. So again, a very simple question. So answer is the equivalent oxide thickness decreases while maintaining the same capacitance. So what it means is EOT is simply how much would be the thickness of SiO2. It will be T high K into epsilon SiO2 by epsilon high K. So even though your physical thickness is higher, but the equivalent oxide thickness is lower for the same capacitance. So that is why we are using high K materials, because physically we are increasing the thickness. The physical thickness is higher, but the equivalent thickness is smaller. So for we get same gate capacitance without increasing for increased physical thickness. So we can avoid the tunneling. Okay, let's see the next one. Choose the correct option from the following statements regarding FinFET technology. A. FinFET offers better electrostatic control over the gate than planar MOSFETs. B. For a similar operating voltage, planar MOSFETs offer much lower delays than FinFETs. So this is obviously option A is true and B is false. Right? It offers better electricity control because it is surrounding the gate on all three sides now. If this is the channel here. So gate is on all these three sides. So better electrostatic control. And FinFET has the lower delays compared to planar MOSFETs because CV by I is actually increased, C and V are decreased in these technologies. So the delay is actually lower in FinFETs. So A is true and B is false. This is option B. Next one. According to the graph on performance enhancement in tri-gate transistors, what happens to the transistor gate delay as channel current increases? Again, we have seen this delay is CV by I. So if I is increasing, the delay will reduce, which is option B decreases. Okay, so next question. For a scaling factor alpha, the supply voltage VDD and doping concentration N scale less. We have also already seen this. VDD reduces and N channel increases, right, by alpha. So it should be option D. VDD reduces to alpha VDD and channel increases to alpha N. Or it could have been VDD changes to alpha VDD. If alpha is 0.7, NCH changes to NCH by alpha. Next question. For the scaling factor alpha, that's delay in the circuit TD scales as. So we have already seen this TD reduces to alpha TD. So this should be last option, option F. Next question. Given below are two statements regarding the current in a short channel MOSFET. Statement 1, the current in for a short channel MOSFET saturates at a larger VDS compared to long channel MOSFETs. Statement 2, the short channel MOSFET reaches the critical field at smaller applied bias leading to velocity saturation. So So again, statement 1 is false, statement 2 is true, and due to velocity saturation for the same reason. A long channel MOSFET, a short channel MOSFET, due to velocity saturation. So statement 1 is false, statement 2 is true. Okay, so these are all the questions I have for today. I hope you understood it well, and please go through the video lectures. And if you have any doubts while solving the assignments or any other questions, please feel free to email me here. So we will not meet for the next 2 Mondays since we have already taken 2 extra classes this week. Our next class will be on 6th of October. Okay, so thank you everyone for joining. We'll meet again on October 6th.